Good afternoon to all. I am Beerbal Solanki, Assistant Professor in AKGC College, Ghaziabad. I will discuss the subject as a tuple, theory of automata and formal language, in which we discuss the unit second, in which we consider the today topic is Arden's theorem and its related numericals. So we start from the starting. This is the unit syllabus, and in which we evaluate the Arden's theorem. We discuss the Arden's theorem today lecture. Now we start the Arden's theorem. So what is the Arden's theorem and what is the statement of the Arden's theorem and its proof? Then R equal to Q plus RP has a unique solution, that is R equal to Q plus QP star. So suppose P and Q. Let's suppose P and Q two regular be the root are a regular expression, and P does not contain the epsilon. Then the R equal to Q plus RP has a unique solution, that is R equal to QP star. So we now discuss about the solution of the proof of the Arden's theorem. So here we starting from the here R equal to Q plus RP. Now put the value of in this equation we put the value of R from here. So Q plus put the value of R, the R equal to Q P ka clean closure. So Q P star and concatenate P. So now taking the Q variable as a common, then here remaining part is that epsilon, and then here go for the common, and the remaining part is this P star P. Now this is the identities from we can write this as a we can write these as a R equal to, suppose R equal to R star P. So it can be write as a R star. So here put these value here, and suppose R equal to R plus epsilon, then it can be write as a simply R. So here the QP clean closure. So here is the solution for that. If this, then we can write this. This is the proof here. So R equal to QP star is a unique is a solution. Now see again this equation R equal to Q plus RP. Now we put the value of R from here to here. The Q plus RP and concatenate P. So now multiply the P value from the between the Q plus RP. So Q plus QP plus RP square. Now again we put the value of R from here to here. So the concatenation of Q plus P R double P. So it can be right Q plus QP plus Q P square plus RP Q power 3. Now it is now again and again put the value of R in which here R. So the Q plus QP plus QP Q to the Q plus Q concatenate P Q power 2 plus that's Q P n Q Q P to the power n and plus R P n plus 1. It can be write as a from here to here. It can see now now we put the value of R or substitute the value of R from here to here. R equal to Q P star. So put the value here. Now this equation remaining. Now common part here we can see from the equation Q, 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 Q and Q. Now taking the Q as a common, so here is the remaining part epsilon, here is the P and here the P square plus that's P to the power n plus P star concatenate P Q power n plus 1. Now it can be right, how to this can be right? It can be right as a it can be right as a here P to the power P star or P clean closure of P. So Q concatenate P star. Here is the R equal to Q P star is a unique solution for that. So here we discuss about the statement of Arden's theorem and the solution and the has a unique solution and the proof of that and also the proof of that. Now we discuss the next part and that is the next part is the numerical part of the Arden's theorem. So we see the numerical related numerical according to the Arden's theorems, or we can define the DFA. It can be write as a DFA to regular expression. DFA that is the determinist finite automata to regular expression. Here we see now the conversion of DFA to a regular expression, and now see how to write the DFA. Here this is the representation of the DFA for the language. So here given the Q1 is the initial state, and also this is the final state. Here it represents the initial state and A is a input and B here is the input and Q1 is a next state and take the input B and A and B and Qt is also a state. Now how to write the regular expression for the given DFA. So one by one we see how to write the regular expression. Firstly we write the regular expression from the how many are the state. So simply we write the regular expression from the given language. Here Q1 is the given Q1 is a state. So write here and write how to write the right part. We we can write suppose Q1 is a write the regular expression for the Q naught state. So we see we can reach the Q naught state from Q naught to Q naught by taking the input A, and also we reach the Q naught state by taking the input A to the state Q2. So here we can see Q naught take the Q naught state and give the input A. So we reach at the Q naught state plus, and remaining we can see we take the input A at the at the state Q2 and we reach the Q naught state. So here we can write, and also the Q naught is the initial state. So we write here as a input epsilon. So we reach at the Q naught state, and write the similar equation for the Q1 state. So Q1 equal to how to reach the Q1 state from the different state. Take the input Q naught. We take the Q naught, take the input A and take the input B. So we reach at the Q1 state plus uh, plus we give the input B at the state Q2. We reach the state Q1 also plus we can reach Q1 state if we give the input B at the same state it also, and now write the equation for the Q2 state. So is we can reach the Q2 state only if we give the input Q1 state, we give the input A at the state Q1. So Q2 is Q2 equal to Q1 dot A. So we reach Q2 state. Now we find out the regular expression with the help of the equation given. Suppose this is the equation 1, this is 2, this is 3. Now we find the regular expression, we target we find the regular expression to the state Q naught, because Q naught is a Q naught is the final state. Suppose here Q1 plus Q2 also Q1 is also the final state. So we write the regular expression for the Q1 plus Q naught plus Q1. So here is only the Q naught is a initial state and final state. So right, we convert all the equation into the form of Q naught. The all equation converted into the form of the Q naught, or it is the Q naught is the final answer for that. So now convert these equation into the form of Q naught. Suppose here we take the equation 1, equation number 2. So equation number 2 is that Q1 equal to Q naught B plus Q1 B plus Q2 B. Now the substitute the value of the Q2 value is that from the equation, from substitute the value equation and 3 that is Q2 equal to Q1 dot A. So Q2 value is substitute here is that Q1 dot A B. Q naught B plus Q1 B plus Q1 A B. Now take the common value Q1, Q naught B plus Q1 common, here the remaining part is B plus AB. Now we apply the Arden's theorem in this equation. Suppose this is the R, this is Q, this is R, this is suppose this is R, this is R, this is Q, this is R, this is P. Now the solution of that, R equal to Q P star, R equal to Q P star. This is the solution of that. So Q1 equal to Q naught B. This is suppose as a P. So B plus AB to the power clean closure or star. So here is a solution of Q1, and now we take the equation number 1, Q naught equal to Q naught A plus Q2 A plus epsilon. Now put the value of Q2 into the equation that, and Q2 value is again equal to Q1 dot A into the Q1 dot into the equation here. Now Q naught A plus Q1 A plus epsilon. Now put the value Q1 from here to here. Q naught plus 1, Q naught B plus B plus AB plus AB here the put the value of Q1 B plus AB का clean closure and concrete double A plus epsilon substituting the value Q1. Now Q naught A, now common the value of Q naught. So here the remaining part is A plus B AB, or that is a clean closure, and concrete double A plus epsilon. Suppose again that here this is the Q naught. Suppose here this is R, this is Q, this is R, and this is all is P. Now we can apply the Arden's theorem here. R equal to Q plus RP, and the solution of that again R equal to Q plus RP. So the solution of that R equal to Q P star. Now apply this Arden's theorem here. So Q means epsilon here, and the P is that here A plus B concrete B plus AB whole clean closure concrete double A. This is clean closure of all bracket. Now we can write here apply the identities. Suppose R equal to epsilon R, so it can be write as R. So it can be write also here. So Q naught equal to A plus B bracket B plus AB. This is the clean closure of that bracket, and concrete double A, and the this bracket clean closure. So this is the final answer. So this is the final answer for the given DFA. This is the given DFA can be represented as a transition diagram for the given DFA. So this is the different equation Q naught, Q1, Q2, and this is the input for that, and how to convert this equation into the regular expression. So simply we write the equation for the all state, that is q naught, q1, q2. So here we write the equation, simply equations, and equation can be write, how can write the uh, equation write simple, if we write the equation q naught. So how to reach the q naught state from the different state, take the simple input. Some input is here only a and b, so we can write the equation for the q naught and then q1 and then q2 also. So now target of the uh, this equation, we convert the all equation to the form of q naught. So because q naught is the final state, so we write the regular expression. How to write the regular expression? We convert all equation into the form of q naught. Suppose here q naught and q1, uh, suppose q naught is a initial and final state. Suppose q1 is also the final state. So we write the regular expression for for that q naught plus q1. So here is only the q naught state. So the all equation converted into the form of the q naught. Suppose here the q1 state, and write the and convert the q naught into the different form and apply here the Arden's theorem, and again q naught in convert into the other form and apply the uh, uh, this value q1 value, and uh, we find the answer for the given DFA machine. So this is the solution for the given DFA into the regular expression. Thank now references. So thank you.